So, a very good morning, and let us start. So, in the last class, we have seen the basics of the transmission lines, correct? And we also have the idea about some of the electromagnetic equations, then followed by some of the transmission line equation, time harmonic form we have seen. And finally, we try to fix it out our characteristic impedance out of these things. So it was we were taken assumptions actually that this is a lossless transmission line, correct? Now today we'll be talking about the losses in a transmission line, and we'll see that how it affects the propagation, what are the elements are responsible for the losses and its effect over the propagation, correct? So before that, we'll revise some of the basic things what we studied in the last class. So what we have seen the TEM wave along the parallel plate transmission line. So we opted a very basic transmission line structure, and we written number of equations actually. And if you see, so we came across that initially we tried to fix it out, that what is the surface current at the lower plate and the upper plate. This was the structure, if you remember, correct? So this was the structure of the parallel plate transmission line, and it was assumed that we have taken the Y polarized electric wave to solve this, and particularly we are going to solve for TEM wave. And then after we fixed its magnetic fields from given electric field, and after that we have written the boundary condition as well, correct? After having the boundary condition and the idea of the electric and magnetic fields, so one can easily fix it out the surface current, like you can show here. You can see these things. So particularly if you see, we have written all the things in terms of electric field, fine, at lower plate as well as at upper plate, fine. So these were the two surface current actually, fine. Then after we carried out the discussion and we solved the two very important equation which we called as a time harmonic transmission line equations. And here these are minus d Vz over dz is equal j omega Li is a function of z, and the another one is minus di over dz is equal j omega mu Ey. So these were the two equations which we called as a time harmonic transmission line equation, fine. Then what we found that these equations are the coupled equation. Why I'm saying the coupled equation? Because these are the two parameters, correct? Now the thing is we need to decouple it. So how we will do? We have to again differentiate. We have to again differentiate with respect to z. So if you do so you can write the two very important equation. This is a similar kind of wave equation if you compare with the electromagnetic theory. So this is a kind of wave equation, and particularly we found we selected the solution in terms of exponential form because we are dealing with the propagation. Then after what we have seen that having the solutions like this, we can also fix its characteristic impedance, and its characteristic impedance is coming out as under root L by C. And finally we wrote the things in terms of the geometrical dimensions of the parallel plate transmission line, which is Z0 is equal d by w into eta, where eta is a intrinsic impedance. And what is Vp? Vp is a phase velocity, which is omega by beta. And we have seen this is 1 upon under root LC. So these things we have seen in a last class, correct? Now today what we will do, we'll utilize all these outcomes and we'll try to understand what are the different losses associated with this parallel plate transmission line structures, and how we will deal, how we fix the expression for the propagation, correct? For that, we'll recall the quantum vector theorem. So let us start. So today we'll see lossy parallel plate, transmission line. So now the thing is, alpha will be there, correct? Alpha will be there, and here we have to define this G. What is G? G is a conductance per unit length across the two plates. And what is R? R is here the resistance per unit length of two plates. So here the G actually is means for the dielectric losses, and the R for the ohmic losses, which coming from the plate, and G is coming across the two plates. Now if you divide the losses actually, so losses could be seen first the dielectric losses, another one is conductor losses. It is quite clear. So let us see first, which is dielectric losses. Fine. So when we are dealing with the dielectric losses, a very basic formula actually should come in our mind, what we learned in 10+2, which was C is equal Q upon V. I hope you can recall this formula. Is very important to fix the capacitance. Now the situation is similar if you see this two parallel plate transmission line particularly. So there are two plates in between. We have a dielectric media or maybe air. So there must be some capacitance. So to understand what are the dielectric losses, it is better to recall or better to start with this equation, which is C is equal Q by V. Now, how we can express in terms of the electromagnetic parameters, like in terms of the electric field, in terms of the magnetic fields, D, okay? So if you can expand, so the first you can write as closed integral d dot ts divided by minus E dot L. So this is a very basic things we recall. If you see, this is a Gauss law. Another is that we define E dot dl is equal V. or we can also express the numerator as epsilon E dot ds. Fine. And this is same. Now we written capacitance in terms of the material parameter as well as the electric field. Fine. Now how we can express the resistance? So a very common definition we studied and frequently we are using, which is R is equal V upon I. Now in a similar way we can also express in terms of electric field as well as surface current. How we will do? E dot dl divided by, and this is J dot ds. So these are the basic electromagnetic relation you can recall, or you can also express what is J? J is the surface current density, and we know the Ohm's law particularly, and we can write the sigma E dot ds. Now if you see, we have a two very good relations. One is a C, another is R. So better to multiply these two. Let's say this is equation star and this is equation hash. So let us multiply these two outcomes. So when you multiply these two, R into C, so what will happen? Some of the term will be cancelled out, correct? Some of the term will be cancelled out and you will remain with RC is equal epsilon over sigma. This is one relation we got. Or we can also express it C by G is equal epsilon over sigma. So we can also write this G is equal sigma C over epsilon. So this is one thing. Please note it down. Now what is next actually? We know that C is equal epsilon omega by D. This relation we have seen. So we can also write G as sigma W, sorry, by D. This is in Siemens per meter. So basic relation we established here, if you see. So now we have a relation R and C, in between R and C, C and G, in terms of the given parameters. Correct? Now what is next? After having the idea of these parameters, we supposed to know the power flow inside the parallel plate transmission line. And how we will see these things? If we better recall the pointing theorem, because pointing theorem will provide us the idea that how the power flow is going to be happen. Fine. So let's do for average Pointing vector. How will define? P average is equal to half of real part E cross H. What is we are missing here? Star. And we are taking the real component of this. Fine. So if you try to expand this and solve, so what we can write particularly, we know what are the component of E we have and what are the component of H we have. So better to expand first and then we'll see that what terms are coming. Now here we have to take care a non-vanishing axial electric fields. What is that? I'm saying non-vanishing axial electric field, which is what? Ez. However, for the TEM wave, we have seen the Ez and Hz become 0, and we also seen the Ez is 0. But the thing is, when we are taking some short of the losses, ohmic losses and all, so there must be some effect, and we should not forget about these non-vanishing axial electric field. So we'll take into account to solve the derivation. So particularly when alpha is not equal to 0, then I'm saying this thing. Now, if you expand this average power, how it will look like, let us see. So this is half real part of, now how many component of E we have? So we started with the EY component, and then we have seen that we have HX component. And finally, because we have alpha is not equal to 0, there are losses actually we are considering while the propagation. So we are saying that there must be some small effect of these axial electric field must be there. So that is why we are incorporating here what? Ez also. Correct? So how we can write these things? So E could be expand as AY EY plus AZ EZ. Correct? What I'm saying? This is AY cap EY plus AZ cap EZ. These are the two components. So this is actually this EY we started, if you remember, we taken the Y polarized wave, that is why the EY concept came, and then we fixed our magnetic field and it was HX. So now H component will be AX cap HX star. Now we're supposed to solve these things. Okay, so we can deal with these things, and if you do one step further, so we can easily write that AZ cap half of real part EY HX star plus AY cap half of real part of EZ HX star. These are the two things. I hope there is no issue with this. So let us try to understand what these things are. So a very first term, which is this, is actually power flow in Z direction. What is that? I'm writing here power flow in Z direction, which is actually required. Fine. And what is this term? This actually contribute the ohmic losses. Like here you can see the axial field and Hx is there. So definitely this will provide the ohmic loss, and the origin of Ez is like that because we cannot forget these non-vanishing field because of these losses, ohmic losses and all. So we need to have these things, correct? So we don't have the options. So this particular term is going to contribute in the ohmic losses. Fine. So this is the thing. Now here, if you see, there are two components we are getting power. One is a AZ component, another is AY component. AX is completely zero here. And what we are saying that power flow in that direction, and that is actually required. Another term we are saying this is ohmic losses, but there is a AY component is there. It means that there are some disturbance or there are some flow in a Y direction as well. Correct? So that is why we have to accommodate this axial ratio, and we got this result, and we can explain the physics behind this actually. Now, after having this idea, we can define the number of terms, what they are. The first is the surface impedance. So what we have seen so far, which is a characteristic impedance. Fine. Now I'm saying that surface impedance. So this is a different term. Don't mix with this. Surface impedance. And how we are going to define it? That this is the ratio we are defining as ZS, and ratio of ET over JS. What is ET? ET is a tangential component of electric field. And what is JS? JS is a surface current density at the conductor surface. Fine. Now, let us consider the upper plate only. So, what we can write if you are considering the upper plate, of this parallel plate transmission system. So, we can define the surface impedance as Ez over surface current density at upper plate, JSU. JS stand for the surface current, and U stand for the upper plate. This is equal to Ez over Hx. We have a very proper relation between J and H. From there, we can write Hx. And this is equal to eta C. Eta C is what? Intrinsic impedance of the plate. Now, let us discuss over this intrinsic impedance of a good conductor. C stand for the conductor. C stand here for the conductor. Actually, we are discussing about the conductor. So, eta C is, we can also express it at mu over epsilon C. As we know, for the conductors, the real part must be 0. Fine. Or we have the definition of this, epsilon C is equal to epsilon dash minus J epsilon double dash. Also, we have sigma is equal omega epsilon double dash. Now, from these definitions, we can rewrite these things as mu over minus j epsilon double dash, because this part is going to vanish for the conductors. And finally, you can rearrange all the elements, and finally you can write j omega mu over sigma. So this is what? This is intrinsic impedance for a good conductor. Now, so we were started from the surface impedance, which is ZS, and we know this impedance could be written in terms of the real and imaginary part as RS plus JXS, or here this is equal to eta C. Fine, we have seen in our previous definitions, and eta C we already have. Better to put C. Fine. So let us recall these things again, and we can rewrite it as under root 2 pi j f mu c. What we did actually, we expanded actually omega 2 pi f divided by sigma c. Now the thing is, we can also express this particular term as 1 plus j under root pi f mu c divided by sigma c. This is what? This is ZS. How we did these things? So we know that under root of j we can express like 1 upon under root 2 1 plus j. So these things this relation we utilized actually above, and we got this relation. So what is the need of this? Because we want to separate out what are the real terms and what are the imaginary terms, because the definition is like this, right? So we have very good relations, and we are going to connect so many things. Now let us consider the second term of the Poynting vector, which was P average in a y direction is equal to half of real part Ez Hx star. This was the thing, remember? So what I told earlier, this is going to contribute in your ohmic losses. Fine. And if you see this thing, this is P average in a y, so there must be some flow in a y direction as well. Now let us expand this. We have so many relations and we can utilize these relations. So this will be half real part of Ez. How we can write Ez? We have a very good relation between the Zs and Et. Fine. And what is Et? It is a tangential component, which is Ez. Now, so better to write this Ez in terms of Zs and Js. So here I am writing for upper plate only. So ZSU, Zs, and this will be Hx will be ZSU star. Fine. It's quite straight. Now, if you further rewrite this thing. So you can write half mod of J SU to the whole square RS watt per meter square. This is what? This is P average in Y. And why we written RS actually? Because we are dealing with the, because we, if you check here, we remove this real part. And when we are taking the real part actually, so we need to incorporate only RS, which is which contribute the real only. The imaginary we are not taking, because we have to take, the definition is like that. Fine. So now we have a very good relation, or we can estimate the power, average power in a y direction by this formula. Now let us see the ohmic power dissipated in a unit length of the plate having with W. So how we will write these things? That P sigma, I'm talking about the ohmic power dissipation per unit length of the plate width, which is W. So P sigma will be W P average Y. This is the relation we're supposed to use. Now, if you recall the above relation, so finally you can write half of W J S U to the whole square RS watt per meter square, watt per meter, because we are going to multiply with W, correct? Now, how we can define the currents then? So I will be W J S U. So finally, one can easily write P sigma as half of I square RS by W. So what we can see here, or what we can say actually, the power dissipated when a sinusoidal current of amplitude I flows through a resistance. This is a similar thing what we studied in a circuit theory as well, if you remember these things. So we calculated, this is for the upper plate. Fine, we calculated this for the upper plate. Now RS actually we taken here, sorry, for the upper plate actually. So the thing is, we need to think about the total one. So how we can define these things? So R will be 2 times of RS by W. So the total series resistance per unit length, I would say this is a total resistance per unit length, series resistance. Why I'm calling series, I'll tell you these things in a coming classes. Fine. Or we can also actually guess, because ohmic losses due to here the plate, and the plates are running in a z directions, correct? So when we make its equivalent circuit, so the R will be coming in a series. I'll explain other way around in the coming classes. So what we can write actually, finally R will be 2 by W. This is W, correct? With, don't confuse with omega, because omega we written in terms of now 2 pi f, that is why. This is pi f mu c over sigma c. So this is what? This is your series resistance per unit length. for both plates. We taken the 2 here actually. That is why I am saying this is for both the plates. Correct? Now, so if I summarize these things, so what I can write? We already have the relation of for L, which is mu d over W. This is Henry per meter. Another was we have the relation for G as sigma W over D Siemens per meter, and what is next one, which is C. C is epsilon W over D. This is farad per meter. So what is this actually? So now we have the 4 relations. Finally, we got the 4 relations, correct, or the lumped form, I would say, for this distributed system, which is parallel plate transmission line. So the thing is, we are very much comfortable with the circuits. We have seen in the previous classes as well, we tried to written all the time equivalent circuits, and we written in terms of R, L, G and C, and we try to find it out the output parameters. Now similarly, what exercise we performed here, we got these lumped element for the distributed system. Now alternatively, I can say that for the distributed system, we are going to model with its equivalent circuit, and that is how we will do our life comfortable, because if we are dealing with electric and magnetic field, definitely we can solve, and we can get the outcome as well, but somewhat you have to do a little bit extra exercise. But at the same time, if you can manage the things in equivalent circuit, definitely you can do easily, because in undergraduates we are very habitual with these circuits, how to solve and how to apply the different theorems, KVL, KCL, Thevenin and all the things. So better to write in this way. So that was the idea actually, that within these 2 classes we have seen that how we can write the lumped parameter for these distributed system. So this is all about for the parallel plate transmission line. Fine. So if you have any questions, we can discuss now. Correct?